Cool. Time for the next talk. This one is on the Keystone assembler framework.
Okay. Okay, so welcome to my talk. And this one's about Keystone, the last missing framework for reversing. Actually, the title is just to catch your attention, so don't dig too much into that. And Keystone was already released with all the source code, binary package, and documentation at the website, keystoneengine.org. You can get that from the website. Okay, so my name is quynh, and I have some background in academia. And my main research focus on operating system, virtual machine, binary assist, and on those low-level stuff. And I happen to be the founder of a few frameworks: Keystone disassembler, REcon emulator, and Keystone assembler. So that's a question. Anybody here use any of those frameworks? Oh, thank you. Okay, so in this talk, I will introduce a bit on the background of the assembler frameworks and the issues. And next, I introduce the motivation behind Keystone projects and how Keystone was designed and implemented. And there are a few demos if you have enough time. Okay, so all the reversing tools are based on some fundamental foundations. One of them is a disassembler. The second one is CPU emulator, right? So what is missing here? So we look at the picture again, you see that disassembler, given the input as a binary, you return the instruction in assembly. You give the same binary to emulator, it runs the instruction and tell you how the CPU is affected. So the question here is, where is the binary coming from? And the answer is that mostly the binary comes from some assembly instruction, and you need to compile that to get a binary. So the missing pieces in this picture is the assembler. So you can see that with an assembler, you can compile assembly instruction, get back the binary, and you can feed the binary to either disassembler or CPU emulator. So assembler is something very simple. It compiles the assembly instruction for you and return the encoding, usually as a sequence of bytes. First of all, on x86, if you compile inc EAX, it return you 1 byte, which is 40. And the CPU can understand this byte 40 as something that increase the EAX register by 1. And here we focus on framework, not just assembler tool. So framework is something that more or less a library which you can embed in your tools and build your application on top of the framework. So assembler has some important application, and the most important one is dynamic machine code generation. So we can compile a runtime the assembly instruction and get back the binary. And usually you use assembler for something like binary rewrite, binary searching. So on the assembly engine function in the same way inside. So basically you give the assembler one or few instructions. It will pass the input into many statements. And for each statement, the assembler will handle it differently. It can be understood as a label, macros, directive, and so on. For the instruction, assembler will pass it into mnemonic and operands, and after that it emits machine code accordingly to the output from the last phase. And here you need to understand the CPU instruction method very well to do this one, to emit machine code properly. So now what you need to do if you want to build one assembler from scratch? So the answer is the huge amount of work. You need to have good understanding on CPU encoding. You need to understand all the instruction in the instruction set of the CPU. And lastly, you need to keep up with the updated from the CPU vendor because the CPU vendor frequently introduce new instruction. So it's not easy work. So what is a good assembler framework? So here's my definition for a good assembly framework. First one is must be a true framework, which means it allows you to embed framework into your tool without having to call external process. It should support multiple architectures. So support x86, ARM, ARM64, MIPS, PowerPC, Spark, and also on those important and popular architectures. It should be multi-platforms, which means it should work on own cap, OS, Windows, Linux, Mac, Android, iOS, and so on. It should be updated. It should support latest instruction on all those CPUs. And finally, it should have bindings because usually people build tools using bindings, high-level languages like Python, Ruby, Go, JavaScript, and so on. Unfortunately, so far, even in 2016, there's nothing up to my standard. There's also a few frameworks like Yasma, which is only support x86 and nothing else. It's no longer updated. There's something from Intel named Intel Set, which has the same issues. It only supports x86 and nothing else. It comes from Intel, but Set actually misses many instructions. And it's closed, so you cannot fix bug inside. You cannot understand what happened inside when you use it. And finally, there's no framework for all other important architectures. ARM, ARM64, MIPS, PowerPC, Spark. We had nothing for those CPUs. So with our proper framework, people struggle for years and forever. And because there's no framework, they need to build your tools by executing on external process, for example, NASM or GNU gas from GNU. And the way they do is that they feed the assembly code. Okay, they write the assembly code into one file, and they feed that file into the external tools, let it run. After that, they get the object code. And again, they need to call a linker to link the object code into a final files. And lastly, they need to do some need to parse the, for example, EUF file to get out the instructions inside. So you can see that it's a lot of work and it's ugly and it's inefficient. The reason is that you need to call external process, so you consume memory. Performance is bad, and it's not always work. For example, what if we want to do assembler from inside the kernel? It's not a good idea to call back to the user space, right? For the user, for process inside user space. Not nice thing to do. And because you need to call external process, you have little control on the external process and on the output. You don't know what happened inside. And cross-platform support is very poor for all those external tools like NASM or GNU gas. GNU gas doesn't work very well on Windows. It's very hard to compile and to build that on Windows. So I want a good disassembler, support multiple architectures, multiple platforms, always updated and independent. So you can build your tools independently using this framework. So because it seems that if I just sit down and wait for somebody to do this for me, so it will be forever. So because I had so much fun with Keystone and REcon, I decided to step up and do that again. So that's how REcon, how Keystone was born. So I started the Indiegogo campaign for Keystone in March, and thanks to community, a lot of people contributed. And I released a beta code to some beta tester at the end of April. At that time, I had only Python binding. And at the end of May, I released the first version to the public, and the beta tester contributed a lot. They helped to build few more bindings. So we have bindings for Node.js, for Ruby, for Go, and for Rust, and Haskell recently. So totally we have 6 bindings for Keystone now. Okay, so next part is the ideas behind Keystone and how it's designed and implemented. Okay, so we want something multiple architecture, multiple platform, updated. And the core is in C or C++, but the API should be in POC and support multiple bindings on top of that. The issue is that there are huge works you want to do this from scratch because there's too many architectures, too many instructions. Intel alone has like 1,500 instructions. So that's a lot. It has very limited resource because I started this on as a personal project. And I did that for fun only. So my idea is that I do not want to spend a lot of time on this to design, to implement, to maintain it. I want to have own features in months, not years. Because if you want to do everything from scratch, it takes years of your life. So the only way is to stand on the shoulder of the giants at the initial phase. And after that, release a source code to community so people can help to contribute and to maintain it. So the idea that I built Keystone on LVM. LVM is on an open source project on compiler. It has huge communities and very active. And it's backed by many big companies, big CPU vendors like AMD, Apple, Google, Intel, IBM, ARM, IMG Tech, NVIDIA, Qualcomm, and so on. LVM support own type architectures, all the important ones. And it has, it's multi-platform, it's run on own type platform, own type OS. So it's good. So here's an overview of the LVM architecture, which is focused on compiler. So the most important part inside LVM is something called machine code, or MC, which is a component inside the yellow box here. MC is something that is the core of the LVM, which everything else built around it. Compiler, assembler, disassembler, debugger, just-in-time compiler, everything is built around MC. And the central MC is a big table description named table gen that describe all the machine instructions. And they have to name LVM table gen to generate included file for LVM from those table gen files. So the reason I choose LVM to build Keystone because LVM is an assembler framework, right? So it should support inline assembly for compilers, which means it already has assembler inside MC component. But keep in mind that MC is only built and usable for LVM and nothing else. It's closely designed, implemented only for LVM, not for external process, not for external tools. And MC is very highly active, maintained and updated by community, by all those big CPU vendors. LVM is already built in C++, so it's easy to build Keystone on top of that. And to build Keystone, I just focus on those that has those architectures has assemblers. And Keystone support 8 architectures so far. So the advantage of using LVM to build Keystone is that the code has very high quality, done by very good professional programmers. And the assembler inside LVM is actively maintained by all the CPU vendors. Like x86, assembler is maintained by Intel, who's better than them. ARM and ARM64 built and maintained by ARM and Apple. Hexagon maintained by Qualcomm. MIPS maintained by IMG Tech, which is a vendor making the MIPS CPU. System Z maintained by EM, also the CPU vendor System Z. PowerPC and Spark maintained by community, but they are very active on that. So new injection is frequently edited, and bugs are very fixed very easily, very quickly. So because we build Keystone on top of LVM, the bugs can be either reported to us or reported to LVM upstream, so you can port it back later. So do things easy to build Keystone because you can just fork from LVM. It's not, because there's a lot of work. So the first challenge to build our Keystone is that the MC component of LVM is not assembler, but it includes many things inside. It has disassembler, it has bitcode, it has instruction printer, it's a linker inside, and the code is huge, mixed like spaghetti. So what I did is that I keep only assembler code of MC and remove everything else that's not related. And I rewrote some components, but I try to keep the parser, the code emitter, and the assembly backend intact because I want to keep synchronized with LVM when they update those components. So I try to keep them like change as little as possible. And this one important decision. I keep on the code in C++, but I did not rewrite them to C. It's different from Capstone. So in Capstone disassembler, I rewrote all the C++ code to C, pure C, and it took a lot of time. But this time I tried to keep everything in C++, so I did not have to spend time to rewrite them, and it's also easier to maintain and update it when LVM is updated. So I had to decide to make the cut for MC because MC has many different components inside. So I need to make a cut, so I take out only what I need. So the question is why to make the cut, because if you cut too little, you keep many things you don't really need inside. If you cut too much, you end up changing some code or a lot of code inside Keystone, and that make it very hard to synchronize with LVM in the future. So it took a lot of time to read source code LVM, and I think I finally have optimal design for Keystone. I think the cut so it's just enough and make very minimal change to MC. So it's a key flow of Keystone. We have parser in feed the injection representation to code emitter in emit the code, and finally we have something like linker to link on the output from code emitter, and finally we have the output. The second challenge to build Keystone is that LVM compile its binary into multiple libraries. So it has separate libraries for supported components, library for parser, library for table gen, and so on. But what it needs is that we need only a single library that includes everything inside. So what I did is that I need to modify the linking setup of LVM to generate a single library. So we have lib capstone.show.dylib for dynamic share library, or capstone.dol for Windows, libcapstone.a for static library, or capstone.lib for Windows. So the next challenge is code generated by MC is only for linking, not the final code that you want. So they build the relocation object code, and the code is generated for the next phase in LVM for the linker. So for example, if you compile inc, the red injection, you return something like FF0425 and something unknown beside that, after that. Because the assembler doesn't really know what to put there. It doesn't know where var1 is. So only the linker at the next phase knows that. But Keystone need to know because we just want to compile to get the final output. So what I did here is I fix something so I can detect and report the missing symbol. So if var1 is not available, it's missing, I report that this one is missing and the assembly input is not correct. So the next challenge is LVM is the assembler inside MC is not aware of relative branch targets. For example, on ARM, you compile BOX, and the target address, it will return something like that. That's from LVM. But actually, this one's wrong because this instruction depends on where you are, where you position this instruction. So it depends on the distance between your place and the target. So what I did to fix it is to have the API KS ASMA to have it allowed to specify the arrest of the instruction. And I changed the core of the MC, so it retains the arrest for every statement. And I find all the relative branch instruction in all the architectures and fix all of them, so the encoding is properly according to the current and the target arrest. Another challenge to build Keystone is that LVM usually give up and it cannot handle the input. So for example, the red instruction is something wrong because the last one should be some constant, some embedded number. So if you fit the red instruction to LVM, it tells you that this is not an embedded and it exits immediately. So this is a huge problem because Keystone is a framework, right? It should not exit. It should not quit when it cannot handle the input. So actually, this is a huge challenge. It's a lot of work. I need to fix all the exit like that, and I propagate the errors back to the top level API. So the exit can be happen in any phases in the flow. It can be in parser, it can be the co-emitter, it can be even in the linker, the final phase. So fixing this took a lot of time. These are the issues. LVM doesn't support non-LVM syntax. It only supports LVM syntax. But you want other syntaxes like NASM or MASM and so on. LVM has no binding at all. And keep up with upstream code because LVM is very active and it updated the code very, very frequently. So keep up with the change from LVM is a lot of work. So what I did is that I need to extend LVM x86 parser so we can support new syntax. I build Python binding myself before the beta phase. And after that, community helped to build more bindings for JavaScript, for Node.js, for Ruby, Go, Rust, and Haskell. And at the moment, I still need to keep synchronize with LVM when they have the important update, important bug fix. So Keystone can get all those bug fixed and also in those important changes. So you can say that because Keystone is built on LVM, it is the same thing, but actually it's not. So I would say that LVM and Keystone is built on LVM. It can do a lot more. Keystone is an independent framework, a true framework, not like LVM. It's more like a tool than a framework. It's aware of current code position, so Keystone can probably encode the relative branch. Keystone is much smaller in size and much smaller in memory consumption. It's like 10 times smaller than LVM because Keystone removes everything that it doesn't need. It's thread safe, it's more flexible, it supports some uncommitted instruction for x86, and it has many bindings. Okay, so I have a few slides to introduce how to write operation inside Keystone, which is very easy. So we take a look at the slides. Here's a very simple in Python. You define the code here. You set up the engine. This one is for x86, 32-bit. After that, you compile the code. You get back the encoding and how many instructions. That's it. It's very simple. So here's the demo. So on the left side, you see the code, right? On the right side, I need to run that code. And this is the output. So true instruction has 2 bytes. Okay, and a few demos. Sorry, I still have written times. Okay, this one, good demo. So somebody use a tool named PonyPack using Keystone. So the idea is that PonyPack has many things, but it has one function, allow you to build shellcode. So you can describe the high-level operation with the shellcode, and you can translate internally. PonyPack translate all the operation into low-level assembly, and it uses Keystone to build the shellcode for you. And because Keystone support own type architectures, the shellcode builder support own type architecture that Keystone support. So here's the demo. No. Okay, so something import, or in Python import Pony, and then you specify that you want Linux shellcode, right? For ARM, and you compile the shellcode, very simple shellcode, and you return the ARM shellcode, right? If you do the same thing, but you initialize not ARM shellcode, but x86 shellcode, you compile the same shellcode again, and you get back the x86 shellcode. So you can see the power of Keystone. It supports own type architecture, so the same shellcode can be compiled into whatever you want. Another fun demo. This one's fun. Semo is one open source emulator. It's my favorite tool because it combines all of my frameworks, combine Capstone, Unicorn, and Keystone. So what it does is, okay, you see the interface here. You enter the assembly instruction in the box, and you press one button here. You can run all the code, or you run every instruction in single step mode. And at every step, you get back the CPU context. You get back the memory. You can see how every instruction is changed. So how it works internally. Here, if you enter assembly into the lab box, Semo will compile those assembly using Keystone. And it gets back the binary, right? And it feeds the binary into the Unicorn emulator. And the emulator can run those binaries and tell you how the CPU is affected at every step. So it's a very nice tool. So I think it's a very good tool for education. So you know how instruction from all those CPU works. And you can see that because it uses Keystone and Unicorn, so it should work on all the platform. So this one is like you run on x86, but you can still emulate ARM instruction, ARM64, MIPS, and so on. So what's next now? Oh, this one's a bot. Nice one. This morning I found it. So somebody wrote a bot for Telegram. So we send instruction to the bot, and it compile, return back the binary. And there are a bunch of tools built on Keystone now. You can see that from the website. Keystone is a showcase page. All kind of different things: code injection, rope gadget, and so on. So conclusion: Keystone is the next generation assembler frameworks, support on cap, CPU, multi-platforms, very simple and clean API, easy to use, easy to build your tools, open source. And future updates is guaranteed because it's built on LVM. So whenever LVM adds something, update something, I can port it back to Keystone and support. And we say that we are seriously committed to Keystone project, and we want to make it the best assembler engine for community. Okay, so here's the full picture, the final picture. So we have Capstone assembler, disassembler, the unicorn emulator, we have Keystone assembler, and all of them are open source, multi-platform, multi-architectures, with many bindings. And they function independently, but they complement each other very well to make a complete set of frameworks. So we call it a reversing trilogy. Okay, so I bring a bunch of stickers to REcon, but unfortunately, I still only have a few stickers left. So if anybody here wants sticker, come to see me after my talk. Okay, do you have time for questions? Thank you.